Welcome to the session on solution of differential equations using numerical methods. In the previous classes, we discussed the methods which give the solution of a differential equation in a power series. Here, we will describe some of the methods which give the solution in the form of a set of tabulated values. Suppose that we want to solve the differential equation of the form dy by dx is equal to f of xy, given that y of x naught is equal to y naught. For values of y at x is equal to xr, that is x naught plus r into h, for r varies from 1 to 3, etc. Integrating the differential equation, we get y1 is equal to y naught plus integral from x naught to x1 f of xy dx. We integrating this differential equation in the interval x naught x1, then we will get the value of y as y1 is equal to y naught plus integral from x naught to x1 f of x comma y dx. Assuming f of xy is equal to f of x naught comma y naught in the interval x naught less than or equal to x less than or equal to x1. This gives the Eulers formula as y1 is equal to y naught plus h into f of x naught comma y naught. Similarly, for the range x1 less than or equal to x less than or equal to x2, we have y2 is equal to y1 plus h into f of x naught y naught, sorry here f of x1 comma y1. Proceeding like this, we obtain the general formula as yn plus 1 is equal to yn plus h into f of xn comma yn. This is the Eulers formula to solve the differential equation of the form dy by dx is equal to f of xy, given that y of x naught is equal to y naught. This process is very slow, and to obtain reasonable accuracy with Eulers method, we need to take a smaller value for h. Because of this restriction on h, the method is unsuitable for practical use, and a modification of it known as the modified Eulers method, which gives more accurate results, is often used in practice. In the modified Eulers method, instead of approximating f of xy by f of x naught y naught, instead of this approximation, we approximate the integral by means of the trapezoidal rule and obtain in the Eulers method. We just integrate this differential equation between the limits x naught and x1, then we obtained y1 as y naught plus integral from x naught to x1 f of x comma y dx. If we approximate f of xy as f of x naught y naught in the interval x naught comma x1, we obtained y1 as y naught plus h into f of x naught comma y naught. This is Eulers method. Instead of approximating f of x by f of x naught comma y naught, we approximate this integral by means of trapezoidal rule and obtain y1 as y1 is equal to y naught plus h by 2 into f of x naught comma y naught plus f of x1 comma y1. This is from trapezoidal rule. The corresponding iterative formula can be written as y1 n plus 1, that is the n plus 1 approximation of y, which is equal to y naught plus h by 2 into f of x naught y naught plus f of x1 comma y1 n, where this y1 n denotes the nth approximation to y. y1 n means nth approximation of y1. We can start this iterative formula by choosing y1 0 from Euler's formula, that is y1 0 is equal to y naught plus h into f of x naught y naught. With this initial approximation obtained from Euler's formula, we can start this iterative formula. This is the modified Eulers formula. Now, let us observe the geometrical interpretation of Eulers method. We have to solve the differential equation of the form dy by dx is equal to f of x y, given that y of x naught is equal to y naught. Let us take the points x is equal to x naught, x1, x2, etc., where xi minus 1 is equal to h. That is, all these points are of equidistant points. Now, we want to find the corresponding values of y as y naught is x naught and y naught are given, but we want to find the value of y corresponding to x1, means that is we want to find y1, y2, etc. Let the actual solution of the differential equation be denoted by a continuous graph like this. This is the x axis, this is y axis. Here x naught, x1, x2, etc. Now, x naught, y naught are given. Therefore, the point x naught, y naught, which is denoted by p naught, will be on this curve. Now, the equation of tangent at x naught, y naught to the curve is y minus y naught is equal to y dash at x naught, y naught into x minus x naught. This is the equation of the tangent at the point P naught, that is equal to y dash at x naught, y naught means f of x naught, y naught, because dy by dx is the slope. Therefore, y dash at x naught, y naught means f of x naught, y naught into x minus x naught. From this we can write y is equal to, here y minus y naught is equal to f of x naught, y naught into x minus x naught, which gives that y is equal to y naught plus f of x naught, y naught into x minus x naught. This is the tangent at x naught y naught. This y is the value of y on the tangent corresponding to x is equal to x 1. In the interval x naught x 1, in this interval x naught x 1, the curve is approximated by this tangent. Therefore, the value of y on the curve is approximately equal to the value of y on the tangent at x naught y naught corresponding to x is equal to x 1. Therefore, we can use the notation y 1 for the value of y, which is equal to y naught plus f of x naught y naught into x minus x naught. That is, y 1 is equal to y naught plus h into x minus x naught is h. Here we use the suffix x 1 because this is for corresponding to x is equal to x 1. This tangent will intersect at this point, here x 1 y 1, where y 1 is this, y 1 is equal to y naught plus f of x naught y naught into x 1 minus x naught. Here similarly consider this interval and we evaluate f of x 1 y 1. Then we draw a tangent, a line through x 1 y 1 having slope f of x 1 y 1, then which will intersect this line corresponding to x is equal to x 2. Then from the equation of the line whose slope is f of x 1 y 1, we find the corresponding y 2. Then we will obtain this point as x 2 y 2 and so on. Here this error is, this is the error, this point is p 1, this is p 2 and so on, which are the corresponding points on the curve. In this method, the actual curve is approximated by a sequence of short straight lines like this. First in this interval, we approximate this curve by this straight line segment, and the total curve is approximated by a sequence of short straight lines. As the interval increases, the straight line deviates much from the actual curve, hence the accuracy cannot be obtained as the interval length increases. Now, here this error at x is equal to x 1 means this is the error, because the actual point is p 1, we approximated the point p 1 by x 1 y 1. Therefore, this is the error at x is equal to x 1, which is equal to x 1 minus x naught the whole square divided by 2 factorial into y double dash at x 1 y 1, which is equal to x 1 minus x naught the whole square means h square divided by 2 factorial. 2 factorial means 2 into y double dash at x 1 y 1. Therefore, the error is of order h square. Now, in the case of improved Euler's formula, let the tangent at x naught y naught to the curve be p naught a. Let this is our p naught and the tangent be denoted by p naught a corresponding to x naught. This is the point x naught y naught. The corresponding tangent is the line p naught a. In the interval x naught x 1, by the previous Euler's method, we approximate the curve by this tangent. Therefore, we can write y11 means the first approximation of y1, which is equal to y0 plus h into f of x0 y0, where y11 is equal to, in this case, m1 q1, where this is the point m0, here this is the point m1 corresponding to x1, this is our x1 y1, we denoted by q1 as x1 comma y1 1, which is the first approximation by this Eulers method. Now, we calculate f of x1 comma y11, and take the average of, this is the f of x1 y11 means this is the slope at x1 y11. Now, we take the average of the slopes at this p0, that is, we take the average of f of x0 y0 and the slope at q1, that is f of x1 y1 1. The average is 1 by 2 into f of x0 y0 plus f of x1 y11. Now, we draw a line p0d. This is the line p0d through the point p0, whose slope is this average 1 by 2 into f of x0 y0 plus f of x1 y11, that is y minus y0 is equal to 1 by 2 into f of x0 y0 plus f of x1 y1 1 into x minus x0. This is the corresponding equation. This line intersects x is equal to x1 at the point at y1 is equal to y0 plus 1 by 2 into h into f of x0 y0 plus f of x1 y1 1. This line, whose slope is average of slopes at p0 and q1, will intersect the line x is equal to x1 at y1 is equal to y0 plus 1 by 2 into h into f of x0 y0 plus f of x1 y1 1, that is y1 is equal to y0 plus 1 by 2 into h into f of x0 y0 plus f of x1 comma y1 1 is y0 plus h into f of x0 y0. In general, we can write yn plus 1 as yn plus 1 is equal to yn plus 1 by 2 into h into f of xn by n plus f of xn plus h comma yn plus h into f of xn by n. This is the general formula of modified Eulers method. Now, consider this example. We are given a differential equation y dash is equal to minus y, such that y of 0 is equal to 1. determine the values of y at x is equal to 0.01 and 0.02 by the Eulers method. This is of the form, the given differential equation is of the form dy by dx is equal to f of x y. Here f of x y is minus y. In this problem f of x y is minus y. Y naught is equal to 1 means x naught equal to 0 and y naught is equal to 1. Now, we want to find the value of y at x is equal to 0.01 and x is equal to 0.02. Therefore, we can take x1 as 0.01 and x2 as 0.02. We want to find the corresponding y1 and y2 by the Eulers method. We take h as 0.01. By the Eulers formula, we have yn plus 1 is equal to yn plus h into yn dash. That is yn plus h into f of x and yn. Therefore, y1 is equal to y naught plus h into f of x naught y naught, which is equal to y naught is 1 plus h is 0.01 into f of x naught y naught. This case f of x y is minus y. Therefore, f of x naught y naught means minus y0 minus y naught. Y naught is 1. Therefore, minus y naught means minus 1. This is equal to 1 minus 0.01, that is 0.99. Now, y2 is equal to, therefore, we obtained y1 as 0.99. Now, y2 is equal to y1 plus h into f of x1 y1, that is equal to y1 is 0.99 plus h is 0.01 into f of x1 y1 means minus y1, because f of x y is minus y. Therefore, f of x1 y1 means minus y1, that is minus 0.99, because y1 is 0.99. On simplification, we get this is equal to 0.9801, that is the value of y2 is 0.9801. The actual solution of this differential equation is obtained by integrating with respect to x. We will get the actual solution as y is equal to e raised to minus x. On substituting x1 is equal to 0.01, we will get y as y1 is equal to 0.9900 for x is equal to 0.01. For x is equal to 0.02, the value of y is y1 is equal to 0.9802, because e raised to minus 0.02 is 0.9802. Therefore, in this case, for x1 is equal to 0.01, the value obtained by Eulers method is 0.99, and from the actual solution it is obtained as the same value 0.99. In the second case, for x2 is equal to 0.02, from Euler's method the value of y is 0.9801, but the actual solution is, actual value is y1 is equal to 0.9802. Here 02 by Euler's method it is 01. Therefore, there is a small error in this case. Now, consider another example. Solve the differential equation y dash is equal to y plus e raised to x. Given that y of 0 is equal to 0. For x is equal to, we have to solve this differential equation for x is equal to 0.2 by the modified Euler's method. The given differential equation of the form dy by dx is equal to f of x y. Here y of 0 equal to 0, which means that x naught equal to 0 and y naught equal to 0. Here f of x y is y plus e raised to x. F of x y means y plus y means the second coordinate plus e power the first coordinate, which is our function f of x y. X naught equal to 0, y naught is equal to 0. Now, we want to find x is equal to 0.2. Therefore, we choose x1 as 0.2 and h equal to 0.2. By modified Euler's method, the general formula is yn plus 1 is equal to yn plus 1 by 2 into h into f of x n by n plus f of x n plus h comma y n plus h into f of x n by n. H into f of x n by n. This is the general formula by the modified Euler's method. For n equal to 0, we have y1 is equal to y naught plus 1 by 2 into h into f of x naught y naught plus f of x naught plus h. Here x n plus h means x naught plus h, x naught plus h is x 1, comma y naught plus h into f of x naught y naught. Therefore, we get y1 as y naught is 0 plus h is 0.2 divided by 2 into f of x naught y naught. F of x naught y naught means y naught plus e raised to x naught. Y naught plus e raised to x naught plus f of x1 comma, the first coordinate is here x1, second coordinate is y naught plus h into f of x naught y naught. Our function is of the form f of x y is equal to the second coordinate y plus e power the first coordinate. Therefore, from this we can write y naught plus the second coordinate plus e power the first coordinate, that is y naught plus h into, here also f of x naught y naught. Therefore, we can write y naught plus e raised to x naught. This is the second coordinate y naught plus h into f of x naught y naught plus e power the first coordinate, that is e power x 1, that is equal to 0 plus 0.2 by 2 means 0.1 into y naught is 0, x naught and y naught are 0, x 1 is 0.2 and h is 0.2. 0 plus e raised to 0 means 1 plus y naught is again 0 plus h is 0.2 into y naught plus e raised to x naught, y naught is 0 plus e raised to 0 is 1 plus e power x 1 is 0.2. Therefore, on simplification we will get this as 0.24214. This is the required value of y at point 2, that is y 2 as here y 1 0.24214. With this example, let me conclude this session. In this session, we discussed the Eulers method and modified Eulers method. Then we discussed the geometrical interpretation of these two methods and two examples for each. Hope that you have understood this method of solving the differential equation of the form dy by dx is equal to f of x y such that y of x naught is equal to y naught. Thank you for listening the class. Have a nice day.